Good morning. This is the last lecture of the deep learning course of spring 2020. The semester was delayed by a couple of months because of the COVID lockdown. So we are finishing up or wrapping up by the end of June. But today is the last lecture. So I am broadcasting from the rooftop of our house here in Bangalore. It's a cool day. Nice breeze in the back. I think you can see some of the plants blowing in the breeze. I think it's all the southwestern monsoon breeze coming from the southwesterly direction from where I'm sitting. So the topic is a very interesting one. It's a pretty involved topic. I'll try and see how I can simplify something which is extremely complicated. But those of you who have been with me and following this material through the semester would be able to grasp what we're talking about. But it does bring a lot of those concepts together. Okay, so the topic is the last chapter in the deep learning textbook, which is chapter 20 on deep generative models. In my own lecture slides that you might have seen online, I have listed two additional chapters, 21 and 22. And these chapters, 21 is on variational autoencoders, 22 is on generative adversarial networks. The reason I decided to make two chapters out of it is there is a tremendous amount of material in the last few years on this topic. Actually, one could write a whole book on just deep generative models or just these models. This is just a class of generative models. So how can we make sense of this tremendous amount of material is my challenge to present to you what these families are. So again, let's recall a deep generative model is a model that is able to generate samples from that distribution. So let's say X is the high dimensional vector that the real world generates. X represents text, or it represents a high resolution image. So we want to capture it as a distribution, not just by the low level raw elements like pixels. Those are too complicated. But by means of some latent variables, H or Z, we sometimes use H and sometimes we use Z for latent variables. X is always the input. Y is reserved for output if we have a supervised model. In this case, we don't have a Y. It's not a supervised learning model. It is just learning a distribution of Z given X. So the joint distribution is going to be in terms of both X and Z. In terms of the raw pixel or raw inputs and latent variables. And why are latent variables important? Again, because they simplify the description. If you're going to have a very, very high dimensional X, like a million pixel image, that's too high dimensional to capture all correlations and so on. While if we have a latent space that captures the higher level descriptions nicely. So we resort to this higher level, which is what deep learning is all about, right? We have several layers of depth, which captures all the relationships that exist at the lower levels and lower levels. So we can form new objects in terms of these higher level descriptions, right? Like if X's correspond to human faces and H's correspond to all the features of the faces, the eyes and the nose and the mouth and the hair and so on. By just working with the latent space, we can generate new faces with different mouths and eyes and ears and so on. All right, that's just a very broad justification of what latent variables are. So then what are these families again? So these are specific approaches. Even raw representation of X's and H's are too complicated. We can't generate all possible images And there are many serious issues such as the mode collapse problem and so on. So there have been many solutions people have arrived at. So we begin with the first family, which is called Variational Autoencoder, or VAE for short. That's the first family. And to give you an intuition of what is VAE, let's ask ourselves what is autoencoder. Now that is a very straightforward concept. An autoencoder takes an input and converts it into some kind of a higher level representation such that we can use the higher level representation to generate what was input at the output. So we have a picture of a cat as input to the autoencoder, and the autoencoder produces at the output the picture of the cat. Not a very interesting task of autoencoder. It takes something as input, produces the same thing as output. But in the process, it is not copying. It is actually converting the cat into as small a representation as you desire. It's like pushing something through a bottleneck. And so it gets compressed and compressed. So you get some representation, because that's all you're allowing, that the nodes of the network are getting lower and lower, and you bring it to a certain level, and then you reconstruct. So there's an encoder part and a decoder part in an autoencoder. So what you get out of such a network is that whenever you have an input, you can compress it to uh, this intermediate representation. So there's a compressed version of it, which is hopefully a nice high-level representation description of the input. Of course, autoencoder, you can think of it as a variant of data compression, but it's a very different kind of data compression. A data compression algorithm, such as MPEG or JPEG, it compresses the data for fidelity, that you should be able to reproduce exactly what was input and compress it as necessary. Whereas an autoencoder brings it to a representation. Forcibly, it is a high-level representation, and we forcibly don't want it to remember every detail. What are the salient points about the object? So an autoencoder behaves in that manner. Now, so keeping that in mind, we know what an autoencoder, or the AE part of it. What is this variational autoencoder? So the variational autoencoders at first seem similar to autoencoder, but it's quite dramatically different. What it does, it takes as input X and produces a probability distribution over H, the hidden variables. An input causes a distribution over hidden variables. It's not a single value. An autoencoder produces a single point representation, whereas here we actually get a representation in the form of a probability distribution. So what good is it to take an input and create in some high dimensional representation a probability distribution describing the object? You could sample that probability distribution and generate many versions of that input. So wherever the mean of that distribution occurs, you will have a very uh, highly likely representation of the input. And then there are all these other variants that you can produce. So it seems much more flexible, except you are somehow mapping the input to a probability distribution in some latent space, if you will. Not only that, the VAE maps all of that data into a high-level representation whose distribution is Gaussian, and with a mean and a standard deviation, assuming the variables are all independent. It creates such a nice representation from the input, some distribution, and then you can sample from that distribution. And when you sample from that distribution, you can reconstruct. So you need a reconstructor as well. So just like in autoencoder, we have a encoder and a decoder. In a variational autoencoder, you also have an encoder and a decoder. But in between, it's not a deterministic representation of the object. You are getting a probability distribution from which you sample, and from that sample, you can use the decoder to reconstruct the object again. So you'll get some variant. But from that object, you can get many, many samples. You're going to get many, many variants. Of course, it's not learning just based on that one sample. You would have trained it on a whole family. Let's say it was handwritten digits. You would have trained it on a whole handwritten digit family. And the parameters would have been learned. And those parameters play a role in the parameters of this variational autoencoder representation. So the VAE is this intriguing thing that creates a distribution. So as you can imagine, the kind of formulation we go through gets mathematical in the sense, how do you create such a distribution? We need probability distributions. We need P of X, that's the input. We need P of H given X, the probability of H. H is a vector now, which is a latent representation, H given X. And we run into intractability. Some of these quantities cannot be computed because the number of possibilities that you need to divide by to get legitimate probability distributions are too large. So you need approximate inference to play a role. And if you recall, chapter 19, I believe, was about approximate inference, where we talked about how certain distributions, such as the Gibbs distributions, can be restated in terms of the evidence lower bound, or the elbow, which is defined in terms of the Kullback-Leibler divergence between the distribution of the data and some other distribution which is simpler to deal with. So we got the real distribution P that you're interested in, and then we say that's too complicated. So we deal with another simpler distribution Q, and that is easier to work with. And eventually we'll show that these kinds of distributions are so simple that they are all Gaussians or normal distributions or bell-shaped curves in each of the dimensions. So this kind of formulation is going to be needed. We're going to need invocation of distributions. We need invocation of how similar two distributions are. If I give you one probability distribution, think about this. We have a distribution of all the pixels of faces of celebrities. That's a pretty complicated distribution. Of course, we are going to be mapping into some kind of a latent representation where we are not dealing with the actual raw data, but some high level representation. And then we're going to say that distribution is itself complicated. We're going to approximate it by a Q, which creates a distribution which has got to be as similar to P as possible, which brings in some kind of optimization issues. How do you figure out that Q? Can we use that Q to be something which is all variables are independent? That leads us to what's called as mean field inference. This is all meant for inference in terms of mapping to H from X. And so that is some of the things that's going to come into play. All right. So there is quite a bit of material on variational autoencoders. So bear with me. I will give you the highlights because the formulation itself takes some time. And I'll indicate to you where the material is. And then you can explore all the equations to satisfy yourself what's going on. The second half of today's lecture is going to be on the topic of GANs, or Generative Adversarial Networks. GANs have become a whole industry of its own. GANs are being invoked by artists who can create paintings. You can say, whatever photograph you have, I can convert it into a painting as if it was done by Vincent van Gogh, right? Like that. Or you can bring in uh, some other style of painting and say, can you take this photograph and make it as if it was painted by a particular artist? And again, we are dealing with some high-level representation of the original input and manipulating things in that space using features from a style can create what are called as style GANs. There's a whole topic called style GANs. You can create new objects. Creativity, all this comes into play. How neural networks can be creative. Even a simple idea I described earlier on, from one input we can generate a whole distribution, which means I can give you millions of examples from that distribution, none of which are exactly the same as the input. So you can get many variants, and you can work with the hidden representation to create new things. You can interpolate. Like these variational autoencoders, where are they actually used? Of course, one is to be creative. Similarly, GANs are also for that. They are used even for interpolation. Let's say I wanted to write a paragraph of text, and I can use a high-level representation to take that paragraph of text and create a representation. And then I can instruct the program, here is the first sentence of the paragraph, and here is the last sentence of the paragraph. Can you generate all the sentences in between? And it does a pretty good job. We'll take a look at that. So it says, okay, take your first sentence and make a high-level representation. Take a second sentence, make a high-level representation. So we just work on the high-level representations in between, and every one of them has a surface-level representation corresponding to the next sentence, next sentence, next sentence. And you get a plausible story out of it. All right. So a creative thing like becoming a writer can be somehow done by a neural network. So anyway, GANs are the popular topic today by artists and so on because of the very realistic representations they can generate. That relies on a different model than the VAEs of the first part of our lecture today. GANs they do away with what's called as loss functions and so on in the VAEs. They resort to an idea where they have a particular architecture where they rely on the two main types of neural networks. Neural networks can be broadly divided into generative models and discriminative models. Generative models take data, a large amount of data you have supplied, and they can learn a probability distribution of the data, and you can generate new samples from it. Or you can even use it for the other task, which is discrimination, which is a neural network that can take as input and it can classify that input. Of course, there are nice benevolent applications we talk about, like handwritten digits. It can say whether the input is a 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, or it can take cats and dogs and so on and classify into one of them. Those are discriminative neural networks. Of course, there are also these face recognition, and there are controversial things about identifying people and so on. So anyway, there are so many other applications. Uh, so these generative models can be used for both discriminative purposes and for generative purposes. So those are all applications, and our goal is to learn how do they work, what do we need to do with them, and so on. Right. So okay, so that's really the overview. Yeah, maybe I should just add for the GAN again. It's got two parts. It's got the generative part and the discriminative part. The generative part learns from a data set and then keeps generating samples from it. But the samples may not be good enough. It might be generating samples that don't look like the real thing. The celebrity face is off by a lot, or the digits that it can generate, handwritten digits it can generate, are also not looking very realistic or natural. So they impose an additional process, taking the output of the generative model and feed it to another box called as the discriminator. The generator provides a feed to the discriminator. Discriminator has access to the training data that the generator was using. So it knows about the population of the training data, and it knows that the generator is somehow trying to generate those kinds of samples. So you can think of them as one is real and the one is fake. So there's a real data set that came from real objects. And then there is a fake data set created by the generator. And the discriminator's job is to take an input and say, is this real or is this fake? And if it determines that it is fake, then it says, well, you got to do better. It gives that feedback to the generator. And the generator modifies itself. Its parameters are changed based on the signal that it gets back from the discriminator. So it can improve itself. It tries to improve itself in such a way that it can fool the discriminator. It says, okay, I'm going to give you a better example to fool you. But it also knows what is coming back. So in a sense, there is a game being played in this generative adversarial network. The reason it's called adversarial is there are two players here, the generator and the discriminator. Generator's job is to fool the discriminator. The discriminator tries to call out the generator as to how good it is. So it becomes what's called as a minimax game. So you need to specify the problem in terms of game theory. And they keep on arguing with each other, the generator and the discriminator, until they reach some equilibrium where the discriminator just cannot tell that the input was generated by the real data or by the generator. And such an equilibrium is known as the Nash equilibrium, which is quite famous from other areas of engineering. So basically, this GAN reaches a Nash equilibrium. And there are families of GANs. So people have been finding that the one type of GAN doesn't do a completely satisfactory job. And one famous problem with a generative adversarial network is the problem of mode collapse. I mentioned this earlier on somewhere along the way. Mode collapse is when the generator keeps generating samples from the same mode rather than getting samples from across the distribution. So, just think of those celebrity faces. You're going to have all kinds of faces in your data set, different complexions and shape of the nose and shape of the ear, and whether the person has a lot of hair or not, and so on, right? So it is learning from all of these. That's going to be some kind of a probability distribution. And now we are saying, all right, start generating samples for me. It's going to start giving you very realistic samples of non-existent people that somehow it has figured out in these high-level representation. What does it take to represent a real face? Person is wearing a glasses or not? All these kinds of things. Mustache or not? All these things it is figuring out. But a mode collapse is when it suddenly starts preferring one type of face over all others. You're going to have a lot of people with mustaches being generated. And it does not represent those with beards or without mustaches, or men and women and of different skin color and so on. So that's called mode collapse. It is somehow centering on one mode, which means there is a sub-distribution within the large distribution that is just favoring one type. So you want it to generate all kinds, truly representative of the kind of population that you have. So there have been very many clever formulations. One of those, a huge topic on its own, is called the Wasserstein Gann, or a WGAN. The WGAN says, okay, I'm going to try and attack this problem of mode collapse and come up with a different clever formulation. And after all, these are all about probability distributions, and it invokes a particular way of converting a distribution into another distribution based on what's called as a Wasserstein metric. The Wasserstein metric is also sometimes referred to as an Earthmover distance. So if I give you two probability distributions, both are let's say Gaussians on a real line, and I ask you the question, how different are these two? Think of each of those distributions, the bell-shaped curves, let's say, in the case of Gaussian, are two piles of dirt. So if you ask the question, how different are these two piles of dirt? Wasserstein says, well, how many shovels full of dirt do you have to move from one pile to the other? And the shortest number of shovelfuls of dirt you have to move from one to the other. And you count that, how many shovels are needed to make both of them the same. Of course, you have very different distributions. You'll need a lot of shovelfuls of dirt. If they're almost the same, maybe one or two shovelfuls of dirt are enough to change one to the other. And you say, well, the Wasserstein distance between the two distributions is 1 or 2 or 4 or 400 or so on. So that's an interesting formulation of what is the difference between two distributions. And that plays an active role because this whole thing is all about probability distributions of the data. And so there is a particular variant of GAN called a WGAN or a Wasserstein GAN. That's only one of about 100 or more now different types of GANs that exist today, because this is an area of tremendous progress and people are being extremely creative, even keeping track of how many different ideas have gone in is a hard thing to do. So anyway, my lectures cover about half a dozen different types of GANs and some variants. Today, of course, we only have a one-shot lecture on all of these topics. So I'm just going to give you the highlights of the details here. All right. So with that, let me start the lecture proper. I'm going to temporarily unmute you all, but there might be a lot of noise coming in, and then I'm going to mute you all again. All right. My laptop says you're all unmuted at this point, so you can. Okay, so let me go to. Okay, so we have variational autoencoder slides on the screen now, and if anyone can say that they can see the screen, I can continue.
Yeah, we can see the screen.
Fantastic, Shreya.
We can see, sir.
Okay, thank you. Thank you. All right. So
It's fine, sir. Thank you.
Very good. So we are launching here a very big topic. My lectures on variational autoencoders, there are like about 5 parts to it. Each of them could be a lecture. So I'm going to kind of fly through some of this, particularly the math part of it. So let's begin with. So the topics, as you can see, there are 7 or 8 subtopics in variational autoencoders. It begins with what's the generative model. I already mentioned what that is. And general black variational inference. That is, we have already talked about that in approximate inference. And we come across something called as a reparameterization trick, because we are going to be generating a probability distribution out of the input. I think I gave that sense to you already. So you're going to be converting an input to a probability distribution, and then you're going to have to sample from that probability distribution, and you are going to take that to the output through the decoder. And all of this is going to be trained using backpropagation. The standard technique for machine learning is backpropagation, where we take the input, go all the way to the output, let's say in supervised learning, and we say, well, this output is not so good. It doesn't match what it's supposed to be. And we backpropagate saying, okay, so how much are you off by? And we compute derivatives and we start passing it backwards. And we train the network like that. But when you bring in a stochastic element inside the network, saying it is not just value to value to value to value, when we go from layer to layer to layer to layer, suddenly we say there's a probability distribution in between. Well, how are you going to train something value to value? I can always do a chain rule of calculus. And here you are giving me a distribution. And what we do is we use what's called as a reparameterization trick. It says, even though it's a probability distribution, I'm going to represent it by a couple of deterministic values, like the mean and the standard deviation. So even though I'm saying, hey, here you got a normal distribution. It's like a bell-shaped curve with all these data points that are all normally distributed. I can give you that, which is an infinite set of points that are going to be normally distributed. It's not very helpful to describe it like that. We say, well, okay, if you just give me the mean and the standard deviation, that's good enough. I have got an idea of what your distribution is. That's exactly what a neural network does. Saying, although we are converting the data into a distribution, that distribution is no longer going to be in the form of a standard probability distribution, but like, describing it as a mathematical expression for the distribution. We just give it the parameters. And a Gaussian allows the reparameterization trick. Basically, if, to jump to that point, it is saying n mu sigma, which is the standard way of saying what a normal distribution is. N is the normal, mu is the mean, sigma is the standard deviation, can be rewritten as n01 plus mu. N01 is called the standard normal distribution, which means it's got a mean 0, a standard deviation 1. Oh, that's a straightforward. And it has got a parameter of mean, and we bring in sigma also into it. So that is basically the idea of reparameterization. And then the issue of choosing what form for Q and P, that is where all this idea of elbow, evidence lower bound, and so on come into play. And a particular algorithm for doing all this is called auto-encoding variational Bayes, AEVB. This style of working with parameters that are probability distributions has a flavor of Bayesian statistics. If you recall, what is the Bayesian method? Bayesian method never works with parameters that are point values. It always says that there is a certain distribution. I give a simple example of what do you mean by Bayes? Well, when you're going to toss a coin and I want to know what is the probability of heads. Well, a standard maximum likelihood approach is to take the coin and you toss the coin 100 times and ask how many times heads came and how many times tails came, and divide heads by the total number, and you say that is the probability of heads. That's a point estimate of the probability of heads. That is not the Bayesian approach. The Bayesian approach says, I'm going to give you the answer of what is the probability of heads as a probability distribution. What does that mean? It says, well, I have some idea, a prior distribution of what is the probability of heads. Before doing the experiment, I'll say, there is a distribution that it's most likely 1/2. And then there are also other smaller probabilities of it not being 1/2. may not be a fair point. So that's called a prior distribution. I don't even do any experiments. I simply tell you it's a probability distribution which peaks at 1/2 and it quickly lowers down to 0 on either side, right? It's on the higher side or the lower side. Bayesian approach says, okay, you start the prior and you toss a coin, and that gives you experimental results, which forms what's called as the likelihood or the probability of those tosses. And it multiplies the prior probability by the likelihood to give you the posterior distribution, which is I had a prior, I had an idea that this is going to be 1/2. And now after the experiments, I'm going to change my opinion and I give you a posterior distribution, which says I revise my opinion based on what I saw. If you gave me a lot of experiments, then my estimate is going to be largely based on your experiments. But if you give me very few samples, if you say you tossed it only like 5 times, there's very few samples you have given me, in which case I'm going to mostly go by what my prior tells me, because this doesn't merit too much importance. But we combine the two to give the posterior. But the answer then is going to be, what is the probability of heads now in the Bayesian approach? The Bayesian approach says it's a distribution of probability of heads. If you did a lot of experiments, it's going to be pretty confident about it. Otherwise, it says I have a distribution. Most likely it is 1/2. And then this is how it breaks down on either side. So that is the idea of Bayesian approach. Same kind of thing is happening here. We get a Bayesian approach now coming into play. So this is quite tightly tied to Bayesian approaches. And it also has the variational component of it. Variational comes in whenever we're trying to find some kind of a good description. And it's an optimization problem, and it cannot be done exactly. So we use the idea of finding a approximation. And it's the word variational comes in also because it's all based on variational calculus. It's not the ordinary calculus which determines maxima and minima of ordinary functions. In variational calculus, we're trying to figure out what is the best function itself, not the maximum of the function, but among all possible functions, which is the best function. Among all possible distributions, which is the best distributions. So all of that comes into play into variational. And then finally, variational autoencoders. So we got to touch upon all of this to be able to describe what's going on. So anyway, generative model is able to generate samples like those in the training data, and it creates some representations in between. If we trained it on handwritten digits, it can generate examples of handwritten digits. And here is an example taken out of a paper where they say that these were all faces. They're not real people at all. They all look like real people, and they were all face images generated by a variational autoencoder. So those are generative models. So why is there so much interest in this topic today? Interest in VAEs and GANs is deep generative models have increased interest due to amazing improvements. You just saw some of those photos earlier on. How do they work? They rely on huge amounts of data. Of course, you're going to have hundreds of thousands of examples. Well-designed network architecture. These are all very carefully designed ones where we use reparameterization trick and things like that. There are smart training techniques. These are not the standard backprop. And they produce realistic pieces of content of various kinds, such as images, text, and sounds. And sounds, yes, train it on music, Carnatic music, and it will generate Carnatic music for you. All right, so very realistic. So there are lots of examples of pop music and so on generated by GANs, which are quite enjoyable. So among deep generative models, 2 major families stand out, GANs and DA. So you have a choice of which family you could use. And VAE, or Variational Autoencoder, is a directed generative model. It has both latent variables, and it gives us a latent space to sample from. So I'm getting some disturbance from some of the users. I'm going to have to mute. All right. So VAEs emerged as a popular unsupervised learning method. Unsupervised learning methods take data as input and create representations, and doesn't have any label associated with each input. Like in supervised learning, you have, okay, that's an image of a cat. Okay, so it knows it's a cat. So it doesn't have any label in unsupervised learning. It simply has images. All right, VAE and deep learning. A VAE models a data distribution using a collection of independent latent variables. The first statement is saying all it is, a VAE is simply uses some latent variables to create a model. And a deep learning technique is used for learning latent variables in a deep learning VAE. So a VAE is not necessarily a deep learning technique, or a deep model technique, but you can use a deep model to do that. And so it turns out to be a hybrid of deep learning and variational inference. So you got to know all about the architecture of deep learning, layers and so on, and backpropagation, these ideas, as well as the idea of variational inference or approximate inference. Okay, here are some more examples, uses of VAEs. They've been used to draw images, and let's say after it has been completely trained, you input a handwritten 0 as input. It's a high resolution handwritten 0, and it gives you a probability distribution as output, which is using prior training as well as this input. And you sample from that distribution, and then you run it through a decoder, and out comes another looking 0. Not the same thing as the input. It's kind of an increased width. In this case, it looks like decreased width. Okay. And look at the lower image. It is a face without glasses, which has come out as a face with glasses. So it can be useful for all kinds of modeling. What would you look like if you wore glasses, or so on. So they can be used to generate images. They have provided state-of-the-art results in semi-supervised learning. A lot of the problem in today's machine learning is that we have some labeled data, but it's a laborious process. Today, captchas and so on, they try and make you get free labeling by you're telling them what the text is in captchas. So, but that's because it's an expensive process and they want to get some free labor. So semi-supervised learning is, I've got some labeled data, but I've got millions or billions of examples of the world, of all the cell phone images and so on, but I can't sit down and tell you what it says in it. Can you use some labeled samples to leverage it and figure out what it could be? And now you have a much larger data set which can be used for a high quality supervised learning. It can also be used to interpolate between sentences. That's pretty intriguing. There's an example in the next slide. So again, if you scour through the VAE literature, there is a tremendous amount. And a lot of these papers will say, well, okay, all your ideas, where did they get used? And this is an example of celebrity faces generated. There are all kinds of people that kind of look vaguely familiar to you. I think this last one seems to be a version of the former Prime Minister of Britain, Tony Blair. He looks like Tony Blair to me. I don't know if it is a version of Tony Blair. He might have been in the original data set. And look at the second one, which is kind of interesting. Producing synthetic text. Interpolate between points in latent space. Supposing I had two sentences. I want to talk to you. And the other one is, she didn't want to be with him. And can you go from the first sentence to the last sentence? I want to talk to you, to she didn't want to be with him. It is working in latent space now. So the raw input is, I want to talk to you. It has gone into some representation, and we manipulate that representation and generate from it, decode from it, what did it become? So for example, if you go small steps by small steps, I want to be with you instead of I want to talk to you. Then the next one is I don't want to be with you. The next one is I guess some version of I don't want to be with you. That seems to be the same thing. But the last step was she didn't want to be with you. So you have generated sentences in between. And this was another interesting example. My link doesn't seem to work so nicely today. This is the interpolate between MIDI samples that you have music and a particular chord of it, and then you have another one, and then you want to do something in between to generate that. So VAEs can be used for these kinds of things, producing synthetic text, generate faces, generate images, generate music, and so on. Okay, now gets the nitty-gritty hard part. You know, anything so interesting cannot be so simple. Otherwise, it would have been done long ago. There's a lot of sophisticated stuff going on here. So we talk about a simple generative model, which is being shown here as a probabilistic graphical model involving X is the observable data, Z is the latent code that represent the observables. And we're talking about a probability distribution of X and Z, joint probability distribution. So this comes from basic Bayes rule of probability, that the joint probability of P of X comma Z, of both X and Z, that is for any assignment of value to X, the observed data, any assignment of value to Z, the latent variable, is equal to P of X given Z times P of Z. So the first one is called as a conditional distribution. That is, what is the probability of X given a particular value of Z? That is, you know, we'll have to assign the X and Z values into these expressions. This is called a conditional. The second one is called a marginal, P of Z. That is the probability of that Z occurring. So this comes from the what is called as the product rule of probability. There are two simple rules of probability that are used in machine learning: the product rule and the sum rule. Here we are invoking the product rule of probability, and we are representing this by a graphical model which consists of Z, because we are talking about Z as the independent variable here. That's why it's the first node here. And this is X given Z, which is Z is pointing to X. So Z is the parent of X, we say, according to this version of it. X can be an image, a human face. And Z is a latent factor, Z or Z is a latent factor not seen during training, and that explains the features of the face. The coordinate of Z encodes. So what does Z encode? Encodes a happy or sad face. Whether it's another variable can encode it's a male or a female face. We are not going about explicitly saying this is happy, this is sad, this is male, this is female. You just present it, and the architecture goes about figuring out that this is how the data is distributed. Of course, later on we can assign labels to each mode and so on. This picture I thought was useful to make it concrete, the difference between an autoencoder and a variational autoencoder. An autoencoder is a deterministic type of structure. Here is a cat. Here is the same cat. So autoencoder goes through an encoder network, and it is being maybe a convolutional network, and that is being represented into a latent vector variable. So this has become a set of nodes H or Z here. This is X. X is the raw input. And the encoder network converts that into this green stuff, which is a latent variables. And those latent variables can be fed to a decoder network whose sole job is how do you reconstruct what the object could be, and as close as possible to the original. It may not be perfectly this cat and this cat are exactly the same, because it has been compressed out here. It has lost a lot of information, and so there is only so much the decoder can do. But the whole thing has been trained The training the network would be, this should be the output ideally, in which case, go back and forth to change all the values of the decoder parameters and the encoder parameters. And so an autoencoder has created something for you. And what has it created? It has created this green stuff. The green stuff consists of all these latent variables, and you can, if you change anything in the green stuff, you're going to get a new cat or something else. You're going to make changes in the output, but you are now restricting yourself to some high-level features. The mouth or the whiskers or the nose or the eyes of the cat are all being captured over here, and you can create variants of it with an autoencoder. A variational autoencoder is a somewhat similar. That's why it's called an autoencoder. But what it gets in between is quite different. So it goes through an encoder network, and as I said, it's going to create a probability distribution over here. It's not just a simple representation. These are the features. There is some distribution here. And that distribution has a mean vector and a standard deviation vector. Because we're talking about a mean vector, if they're all independent variables, like there would be 100 variables here, those are all independent variables, which means they all have their own standard deviations. They could all be Gaussians, but they all have different means and different standard deviations. Some of them are very spread out and some of them are very peaked. And once you have a normal distribution, you can sample it and say, give me a sample from your distribution. Most of them are going to be around the mean of that distribution. And we take that value, let's say it's something close to the mean, and we run it through the decoder network. It creates a sample now. And this sample is going to create a whole set of variants of the same cat now. Squeeze it or make it bigger nose, whatnot, and because every sample is going to give you something else here. Every sample, right? We can use this after a normal distribution. It's very simple to sample from it. We don't need any fancy Gibbs sampling and things like that. So anyway, this is the difference between an autoencoder and a variational autoencoder. And this is from another paper where they applied VAE to face images, variational autoencoder, Px given Z times P of Z applied to face images modeled by X. So they had a set of images of the face, and now they're manipulating the latent representation. And what they're doing is the latent representation Z can be used to interpolate between facial expression. So they're actually using it to interpolate. I suppose they took photos of this person. Not every one of these was a photograph. And they were able to go from this to this or this to this, and so on. I don't know exactly where the real ones were, but most of these were all interpolations of going from, let's say, a frowning here to a happy face, and it's creating various gradations of frowning to happiness, frowning to whatever, view this way, and so on. So people are having a lot of fun doing this. I don't know what the practical example issue here is, but so these are the kinds of things you could do with these images. So now we try to put it all together. I'll have to give you an overview, that's all, because we want to do the GAN also. So a deep generative model is a model with many layers. So we have a deep generative model is a generated observable. There is Z1 or Z1 through Zm is the code. The code need not be just one layer. It can be several layers. In a deep generative model, there are several layers. So this joint probability distribution of X and Z of all these variables can be written as X given Z1 times Z1 given Z2, Z2 given Z3, Zm minus 1 given Zm, and probability of Zm would be a hierarchy of latent representations, which is mathematically represented like that, and graphically represented like this, the same thing. The probabilistic graphical model. It's a directed probabilistic graphical model. So the math for this says the setup is X is a set of observed variables, Z is a set of latent variables, theta is a set of model parameters. These are all the weights in the network. And a specified joint probability density is given by P theta of X comma Z. It's a distribution of X and Z subject to the parameters theta. Right. So any theta you specify will give you a new distribution. Right. You want to choose that theta such that it truly representative of the X's and Z's in your data set. So the whole problem becomes, how do you figure out that theta? Which means, how do you figure out the network? Which means, how do you learn those and how do you deep learn those? And that's exactly what this is all about. So objectives are infer an approximate posterior over the latent Z. Given X, what are its latent factors? Determine probability of Z given X. So it could be infer an approximate posterior. They say this is going to be a hard problem. So that's where the Bayesian comes into play. When we say posterior, we talk about the posterior probability of Bayesian methods, which says maybe we had a prior probability distribution over Z. Typically, they're going to be assuming a Gaussian, standard Gaussian as a Z. And then we get a posterior Z given X. So we're going to have another interesting thing. This X is going to be a discrete variable. Like all the pixels on your image are all discrete variables. You got like, 1 megapixel camera or 1 million variables. They're all discrete actually. 0 to 255 would be the, and then there are of course the 3 layers RGB for a color image. Z is going to be a continuous variable. And how do you go from a discrete to a continuous is an interesting question. I think the next slide explains that. And so we need to learn the parameters theta. So we need to get an approximate posterior, that's a Bayesian view of it, or we need to learn a maximum a posteriori probability estimate. So it could be like theta consists of a set of fixed values. That's your parameters. But on all of this Bayesian type of stuff, we never believe in giving you one answer and giving you a range of answers saying it's a distribution of all of these values it can take. I'm going out of topic here a little bit, but it's an intriguing topic. How do you get a probability distribution involving a continuous variable and a discrete variable into the same model? So we have an example of a thermostat, and we have a continuous variable Z and a discrete variable X. And Z is the temperature in Fahrenheit. I guess this is a US slide where we still use Fahrenheit rather than centigrade. And X is the thermostat that turns the heater on. So you have a thermostat in your house that is turning off the air conditioner on or off. If it gets very hot, then it turns it on. So the variable X is discrete. It's got only 2 states. The air conditioner is on or off, whereas the parent variable Z, so maybe we can only observe the air conditioner is going on or off. We can't observe the temperature. And there is a latent variable that is taking into account temperature. And here is an example being given. X is X1, and it has values X1 and X0. X1 is 0.9. This is kind of a slightly noisy thermostat. Is 0.9 if Z is less than or equal to 65. Z is less than or equal to 65. I guess this has not been set for heating in India. This is set for the cooling in India. It is set for heating in the US, where we say, okay, if the temperature falls below 65, turn on the heater, it's too cold. And it says, okay, it goes on with probability 0.9. And then probability of X0. So this is the relation. So you can have parent is continuous, child is continuous, and so on. So the same kind of thing goes on with a VAE. So this model makes various assumptions about interactability, big data, and so on. And these sets of slides are about various approaches to variational autoencoders is not necessarily to do with neural networks. You can use EM, mean field inference, sampling-based approximate inference, and so on. Given that I want to do a little bit of, you can see the equations. It's really beautiful stuff. I encourage you to go over all of this. I like it. It brings in Deckelbach-Leibler divergence and so on. That's where the variation comes into play, and the inference is complex, so you end up getting lower bounds, so on, shortcoming of mean field, and so on. And in variational auto encoding, we use elbow, the evidence lower bound. So why chapter 19 is important is because it is going to be used in chapter 20. And all of these VAE training, we're going from X to some kind of a mean and the covariance matrix over here. And there is some kind of a Kullback-Leibler divergence that's going on between N01, that's a standard distribution. And we're talking about sampling over here and decoder from the sample. So this is the same thing expressed mathematically. We saw a block diagram of all of this. And this stuff about the AE, an algorithm called AEVB is VAE is a part of it, more on the reparameterization. So there is a lot to this. And I encourage you to look at all of this. What is the AEVB algorithm and so on, testing, and so on. This is what. Here's a simple example of autoencoding using VAE. This is from a paper by quite an influential paper by an author called Kingma. Maybe that's his photograph here. So he's saying in this variational autoencoder, you're going from an input to the encoder is going to create a probability distribution, which is not a single set of values. It might be that the features are smile, skin tone, gender, beard, glasses, hair color. And there are probability distributions along all of these. They're all independent things. Smile and skin tone are independent. Skin tone is independent from gender, and like that. You know, these are all independent features. And by sampling from here, give me a sample for smile, give me a sample for that. And it could be exactly that, or it could be quite a different looking Kingma over here. So this is what goes on in a VAE. All right, so what are the key insights, the elbow, and so on. So these are all the very interesting papers. And these papers are all fairly recent, and tutorials on VAE and so on, huge topic. Okay, I'm going to have to skip at all of these things. Or VAE in the form of a neural network. Maybe I should do a little bit because there is some interesting stuff there also which I want to. We saw this example already. Okay, this is all some standard stuff. Encoder, okay. So how a neural network can be used specifically in a VAE, gradient, reparameterization, how all that works. I have an example that I worked through. Given that it is past an hour since we started, I'm going to wrap up by giving a little bit on GAN. So as I said, there are two families. There are these variational autoencoders, huge topic. You can become an expert on that topic and a lot of values in it. GAN is another family, and that again says, well, VAE doesn't do something well, and I'm going to try and do it better. VAE's images sometimes are said to be a little blurry. The faces that are generated, this looks a little blurry face. It's not as sharp as I'd like it to be. And GAN says, I can do that better. And like that, it addresses. And then GAN says, oh, there's a mode collapse. Okay. So we're going to have all these variants coming in saying, no, mode collapse is going to be handled. Again, generative modeling, some of these are all self-contained slides for me. Like if I wanted to give a lecture on GANs, I'd say, well, what is generative modeling? A simple idea of generative modeling is, supposing I give you some data, right? This dot, 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 dot. It's all like one variable. And I'm getting all of these values. And we say, well, model this for me. Well, model this for me. That's called unsupervised learning problem. I haven't told you anything about the data, the label, nothing. I simply gave you the data. And it say, well, that looks like maybe a normal distribution with a certain mean and standard deviation. That's the best I could do with the data you've given me. That's a normal here. So we say this is a density estimation method. So you have gone and mapped it into a probability density function here that represents the data. A density estimate, given a density estimation model, I can sample from it and regenerate any new samples you want. But one class of generative modeling methods don't necessarily model the distribution or to give you a probability. If I give you a point somewhere here and say, what's the probability the model assigns to it? I guess it will give you some value. It gives you the probability. That's a high probability near the peak, and that's a low probability away from the peak. You would give a probability. Whereas some models don't allow you to calculate the probability. It simply allows you to generate from it. So these GANs are like that. They're able to generate samples, not infer probabilities. So I have training examples here. I train a GAN, and after I've trained the GAN, I can just generate samples. So here are model examples. These are not real people. They are highly realistic photographs, photorealistic images generated using these GANs. Of course, if it is a mode collapse, it will take this female photograph and it'll give you lots and lots of examples of her or lots and lots of examples of him. But it is not going around giving you samples from all across the spectrum. That's called a mode collapse. But anyway, that's a sub-problem to be handled later. So in a generative adversarial network, there are two competing models. So there is one here with the generator G, say some kind of a neural network, which takes as input a random noise Z. It's a normally distributed random noise, and it goes to the generator network, and out comes a generated face. This can be a pretty bad face because it's not been trained properly. And here are some real faces. You know, there is a data set called celebrity faces. I guess that's what, there may be 1,000 celebrity faces. Somebody collected it and everybody has been using it. There are also other data sets, you know, photographs of bedrooms in hotels. So they went around taking pictures of bedrooms in hotels, what the arrangement of the furniture is. Or these are all photographs of the church spires. They went around somewhere in Italy or something and saw a lot of churches, took photographs of every one of them, create a data set. So it can create new church spires for you. It can create new bedroom arrangements, or it can generate new faces. So anyway, these are real faces. This is what the generator generates. And we have some kind of a arbitrator here which inputs these. Let's say it takes the generated face here, and the discriminator says, oh, that is fake because it looks so bad. It doesn't look like the real face at all. And if a real face comes in, it says, oh, that's real. That's a nice photograph. So when it does, all it is doing is a discriminator. Is it real or is it fake? And that signal saying that was, that I detected to be fake. All right. So it comes back here to this network. It says, well, you generate a pretty bad image that was detected to be fake. Improve yourself. Change your parameters. So it goes about improving it here, saying, I'm going to try and generate a better looking face now. Goal is to keep on changing its parameters until the discriminator cannot tell, oh, that is such a good image you've generated. Although it was generated, I'm saying it's real, but it was really fake. So once it stabilizes, once it reaches Nash equilibrium, because these two are competing with each other. These are adversaries. The generator and the discriminator are adversaries. One is trying to fool the other, is trying to figure out, you know, what was the true source of it. So what motivated this approach is VAE has a limitation in modeling perceptual loss. That is, the resolution was not good enough. And so that kind of thing motivated it. And and then what GAN squared do. So all of this GAN theory. So there are now, one of my colleagues in my own department wants to offer a full course on GANs, right? I mean, that is such a sub topic in deep learning that one could have a whole course on it, because there is a lot of people seeking to know about it and use it in their own domain. And these slides here are about different unsupervised methods, Gaussian mixture models, and here is again the phase data set, how they map into a manifold, so on. So there's a lot of tutorial here on variational methods, VAE, and here are examples of the blurry pictures of a VAE. This is all motivating why we need a GAN. And how do you figure out what is the perceptual loss? When I present one of these blurry images, how can you tell that it is blurry in an automatic way? And so it's very difficult to handcraft a good perceptual loss function. And so in VAE, we use a loss function which takes into account what has been generated and what is the input. And that is how we look at the Euclidean loss. And the GAN says we no longer use a loss function because it's very hard to tell a mathematical measure of perceptual loss. So the approach of the GAN again is the generator network, generated image. Here is a generated image, and which could be fed a real image and the generated image. And the discriminator network can take a real image and says 1, that's a real photograph. And it looks at this image again, that's a 0 because it looks like a generated image. Like that is how these are trained. And again, this is based on a Minimax 2-player game. And a GAN network kind of looks like a standard convolutional neural network of these layers, which this is, I think, part of the decoder here. And a particular version of GAN called DC GAN, which is based on convolutional networks. These are all real images generated by GANs, real looking images. And one can play around with these GANs and do vector space arithmetic. We can manipulate the latent space and take things like man with glasses, subtract the glasses to get man, and you can add a female face and manage to get a female face with glasses, same female face with glasses. You can create these kinds of things. I suppose this is kind of interest to people who are designing glasses maybe. So what would you look like with glasses? So this last diagram is about GANs versus VAEs, and what are the differences between the two, because there are two competing families, and there are some discussions about them. Taxonomy of generative models, and you have GANs over here, VAEs over here. There is also pixel CNNs, so on. It's trying to give an overview of classes of methods. I suppose one wants to be a practitioner and wants to right away jump into, I got this data set, I'm going to create new data and so on. You have to decide, I'm going to use a GAN or a VAE, and what are the advantages, disadvantages, and so on. My slides have some of these references that you can look at as well. Okay, I'm going to stop there, and I will see if I'm able to unmute you all in case. Sometimes I really have a hard time figuring out the controls for unmuting all. I'm going to stop live streaming, and